Welcome back. Let's practice finding area using the cross product. Alright, so here's our first example. We want to find the area of a parallelogram where two adjacent sides are vector v and vector u. Now vector v is equal to 3i plus 2j minus k, and vector u is equal to I plus 2j plus 3k. Alright, so if we want to find the area of a parallelogram given two vectors that are adjacent sides of that parallelogram, all we have to do is take the cross product of those two vectors and then find the magnitude of that resulting vector. Alright, and so more formally, the formula looks like this. The area of a parallelogram, which I represent with capital A sub p, is equal to the magnitude of vector v cross vector u. Okay, and so let's do that. Let's take the cross product of vector v and vector u, and so we'll have vector v cross vector u. And the way that I'm going to calculate that is to use the determinant form. We're going to set up a 3 by 3 matrix and take the determinant of that matrix, where the first row are our standard unit vectors, I, j, and k, and then the second row are the components of v, and the third row are the components of u. All right, the second row corresponds to the components of that first vector, and the third row corresponds to the components of the second vector in your cross product. Okay, so let's write in the components of vector v. They are 3, 2, and -1. Those are just the coefficients of I, j, and k. And then the components of u will be the coefficients of I, j, and k for vector u. So that's 1, 2, and 3. So I will write in 1, 2, and 3. Okay, so now to calculate the cross product here, what we want to do is look at our first row here, and we're going to look at each of these unit vectors one at a time. We're going to start by looking at vector I and cross out the row and the column that vector I is located in, and then use the remaining four values that are not crossed out to calculate a 2 by 2 determinant. All right, imagine that those four values make a 2 by 2 matrix. We are then going to calculate the determinant of that matrix, and that would be equal to 2 times 3 minus the -1 times 2. All right, so here's what we'll have. This will be equal to 2 times 3, which is 6, so we'll have 6, minus -1 times 2, which is -2. And that will be multiplied by I. And then next we're going to subtract another 2 by 2 determinant multiplied by j, and then we're going to add that to another 2 by 2 determinant multiplied by vector k. Now for this term, for vector j, we're going to be looking at vector j in this 3 by 3 matrix, crossing out the row and the column that j is located in, and then using the remaining four values to calculate a 2 by 2 determinant. So we'll have 3 times 3 minus -1 times 1. All right, 3 times 3 is 9, so we have 9 minus -1 times 1, which is -1. And then for our last term, where we're multiplying by vector k, we're going to be looking at k in our matrix, and we're going to cross out the row and the column that it's located in, and then use the remaining four values to calculate another 2 by 2 determinant. So we'll have 3 times 2 minus 2 times 1. 3 times 2 is 6, and 2 times 1 is 2, so we have 6 minus 2. Okay, now if we simplify, this will be equal to 6 minus the -2. That's the same as 6 plus 2, so we'll have 8i, and then we're subtracting 9 minus -1 times j. 9 minus -1 will be the same as 9 plus 1, so we have 10j, but we're subtracting it, so we have minus 10j, and then we're adding that to 6 minus 2 times k, which will be 4k. All right, and so that is the vector that represents the cross product of vector v and vector u. Now what we want to do to calculate the area of a parallelogram where two adjacent sides are represented by these two vectors is take the magnitude of that cross product vector. So here's what we'll have. The area of the parallelogram will be equal to the magnitude of vector v cross vector u, and that will be equal to the square root of the sum of these components squared. So we'll have 8 squared plus -10 squared plus 4 squared, and 8 squared is 64, -10 squared is 100, and 4 squared is 16, and so this is equal to the square root of 64 plus 100 plus 16, And 64 plus 16 is 80, plus 100 is 180. So this is equal to the square root of 180, which we can simplify since 180 has a factor that is a perfect square. 180 is equal to 36 times 5. And you can check me on that. If you plug this into a calculator, 5 times 36 is 180, and 36 is the square root of 6. So we could say that this is equal to 6 square roots of 5. And that right there will be the area of the parallelogram where two adjacent sides are vector v and vector u. And just so you can see what that would look like visually real quick, this is not going to be an accurate drawing for what these vectors actually are within the 3D coordinate system. But if you imagine that we had a parallelogram here, vector v might look like this, and vector u might look like this. They represent two adjacent sides of this parallelogram where they both start at the same initial point. All right, and that should make sense because these are two position vectors, and so their initial point would be the origin. Okay, and so by taking the magnitude of the cross product between these two vectors, we found the area of this parallelogram. We found that it was 6 square roots of 5, which, by the way, if you wanted to know the approximate value, this is approximately equal to 13.4 and some more decimals. Okay, so this is the exact value, 6 square roots of 5, but approximately that's 13.4. And then one more thing to remember here is that this is a measurement of area, so if it had units, those units would be squared. All right, so the area of this parallelogram would be 6 square roots of 5 squared units. Okay, let's take a look at a different example. All right, so next up we want to find the area of a triangle where two sides are vector A and vector B. Vector A is equal to 4i minus 7j plus k, and vector B is equal to negative I plus 5j. All right, so this is slightly different than our previous example. Last time we found the area of a parallelogram using two vectors, but now we are looking to find the area of a triangle using two vectors. And so visually that looks like this. We'll have a triangle that looks something like that, where this might be vector A, and this might be vector B. Again, just like with the previous example, this is not an accurate drawing for what vector A and B would look like in the 3D coordinate system. I'm just drawing a rough sketch of what we're looking at here. We want to find the area of this triangle, where vector A and vector B represent two of the sides, and we calculate the area of a triangle very similarly to how we calculate the area of a parallelogram when we have two vectors representing two sides, or two adjacent sides. In fact, it's almost identical to how we calculate the area of a parallelogram, except we divide it by 2. All right, so the formula looks like this. If the two sides of a triangle are represented by vector v and vector u, then the area of that triangle is equal to 1/2 times the magnitude of the cross product between those two vectors. All right, so in this case, the area of the triangle will be equal to 1/2 times the magnitude of vector A cross vector B. And you can also do vector B cross vector A. The order there isn't going to matter since we're taking the magnitude of the resulting vector, right? The only difference between A cross B and B cross A is that this will be the negative version of this vector. All right, so B cross A would be equal to negative A cross B. And so the order in which you do a cross product typically does matter, but since we're taking the magnitude of that vector, it really doesn't matter, because when you take the magnitude of a vector, you square all of the components, and so all of those values become positive before you then take the square root of their sum. All right, so it doesn't matter which of these two cross products you calculate when calculating the area, because you're going to get the same answer either way. All right, and that would be true when calculating the area of a parallelogram using the magnitude of a cross product as well. Okay, I didn't mention that in the previous example, but I thought I would mention it now. But to get back to this formula here, the reason why this is true, the reason why 1/2 of the magnitude of this cross product is the area of this triangle, is because this triangle would be 1/2 of a parallelogram, right? You can sort of imagine that we could have a full-on parallelogram here, and the other half of it is exactly the same size as this triangle that we want to find the area of. So, by finding the area of the parallelogram using the magnitude of the cross product, and then multiplying it by 1/2, we get the area of this triangle. Okay, so I hope that makes sense. When you're finding the area of a triangle using the cross product, you're just finding the area of half of a parallelogram. All right, assuming that the two vectors you're given are adjacent sides of that triangle or parallelogram. Okay, but enough about that. Let's work on actually finding this area. The first thing that we need to do is take the cross product of vector A and vector B. So let's do that. We'll have A cross B is equal to the following 3 by 3 determinant. We're going to have vector I, vector j, and vector k. And then the second row will be the components of vector A, and the third row will be the components of vector B. All right, always remember that the components of the first vector in the cross product make up that second row, and the components of that second vector in the cross product make up the last row, or the third row. All right, so the components of vector A are 4, -7, and 1, the coefficients of I, j, and k. So we'll have 4, -7, and 1. And then for vector B, notice that we don't have a term with k, so that means that the z component is 0. So we have -1, 5, and 0 for our x, y, and z components. So write -1, 5, and 0. And now we can work on calculating this 3 by 3 determinant. We'll start by looking at vector I. We're going to cross out the row and the column that it's located in, and then use the remaining 4 values to calculate a 2 by 2 determinant. We'll multiply -7 times 0 and subtract 1 times 5. Now -7 times 0 is 0, and 1 times 5 is 5, so this will be equal to 0 minus 5, and then we're multiplying by I. All right, that vector that we crossed out the row and the column that it was located in to get that 2 by 2 matrix. All right, then we subtract the next term, or the next component of our vector, and to get that, we look at vector j, this vector right here. And so what we'll do is cross out the row and the column that it's located in and use the remaining 4 values to calculate another 2 by 2 determinant. So we'll have 4 times 0 minus 1 times -1. 4 times 0 is 0. 1 times -1 is -1. So we have 0 minus -1, and then we multiply by j. All right. Since j was the vector that we crossed out the row and the column for, that's what we multiply by. And then finally, we'll have one more term, but for vector k. And so let's look at vector k here. We're going to cross out the row and the column that it's located in and use these 4 values to calculate a 2 by 2 determinant. So we'll have 4 times 5 minus -7 times -1. Now 4 times 5 is 20, and -7 times -1 is 7. So we'll have 20 minus 7. And now if we simplify, this will be equal to -5i minus j plus 13k. All right, 0 minus 5 is -5, so we have -5 times I. Then we are subtracting 0 minus -1. 0 minus -1 is the same as 0 plus 1. So we have 1j, but then we're subtracting it. So we just have minus j. And then we have 20 minus 7, which is 13. So we have 13k. All right, so that's the cross product of vector A and vector B. Now what we want to do to calculate the area of the triangle is take 1/2 times the magnitude of that vector. So we're going to be multiplying 1/2 by the square root of the sum of these components squared. So we'll have -5 squared plus -1 squared plus 13 squared. All right, -5 squared plus -1 squared plus 13 squared. And that will simplify to 1/2 times the square root of 25 plus 1 plus 169, right? -5 squared is 25, -1 squared is 1, and 13 squared is 169. 169 plus 1 is 170, plus 25 is 195, and the square root of 195 does not simplify any further, so what we're left with is the square root of 195 divided by 2. And that is the area of this triangle where 2 sides are vector A and vector B. Okay, now if you didn't multiply by 1/2 here, if you just had the square root of 195, that would be the area of the parallelogram where vectors A and B are 2 adjacent sides. But since we wanted to find the area of a triangle, we take 1/2 of that area. Okay? And then of course, if you want the approximate value, this would also approximately be equal to 6.98 and some more decimals. Okay? And so that would approximately be what the area of that triangle is. And once again, both of these answers, whether you use the approximate value or the exact value, they represent a measurement of area, so their units would be squared. All right, so the area is the square root of 195 divided by 2 square units. Let's take a look at another example. Hey there, real quick, before we take a look at the next example, if you find my tutorial videos here at JK Math to be helpful and you want access to more content such as exclusive bonus videos and dark mode versions of my videos, I'd invite you to check out my membership site, JK Math Plus, where all of that content is available. To learn how to join and see a full list of everything you'd get access to as a member, you can head over to jkmathematics.com/plus. I'll have a link for that in the description of this video. Okay, so if you're interested in becoming a member, feel free to check that out. It's a great way to support me and the tutorials I make, as well as a great way for you to learn math better. But for now, let's get back to the video and take a look at the next example. Okay, so next up we want to find the area of a parallelogram that has the following vertices, and we have 4 different points, A, B, C, and D. Point A is the point 2, negative 3, 1. Point B is the point 6, 5, negative 1. Point C is the point 7, 2, 2. And point D is the point 3, negative 6, 4. Okay, so this is a slightly different problem. First of all, notice that we are working with a parallelogram again, so we're not going to be dividing the magnitude of our cross product by 2 in this case. We're not working with a triangle anymore. We have a full-on parallelogram, but as you probably noticed, we don't have any vectors to work with, or at least not right away. We're going to have to find those vectors ourselves. And so what we have to do here is work with these given points, or the vertices of this parallelogram, and create some vectors between them. Now we only have to make 2 vectors. We could make more, and there's a bunch of different vectors that you could choose to make. But when you do a problem like this, typically what you want to do is choose one point to be the initial point of both of your vectors, and then just choose 2 other points to be the terminal points of each of the 2 vectors that you want to use. All right, so let me show you what I mean visually, just so that we're all on the same page here. Let's say that our parallelogram looks like this, where right here will be vertex A, and here will be vertex B. This is vertex C, and this is vertex D. And I'm just assuming that that's where those vertices are. This is not going to be an accurate depiction of what our parallelogram would look like if we were to graph these points in 3D space. We don't have to do that. That's not necessary. I'm just drawing a rough sketch here. In fact, these points might be located in different spots. This might not be exactly how this parallelogram works, but it's actually not too important because no matter what 2 vectors we decide to use, as long as we pick them from the same initial point, mathematically, through the cross product, the area will be the same. All right, so in this case, what I'm going to do is I'm going to choose point A, or vertex A, to be my initial point of both vectors. So that means that I'm going to be looking at vector AD and vector AB. Those are going to be the 2 vectors that I'm going to find and then take the cross product of to then find the area of this parallelogram. Okay, but you don't have to pick the same initial point that I chose here. I chose to use point A because that's just what I decided to use, but you could have chose to use vertex B as your initial point and use vectors BA and BC, or you could choose point C and use vectors CB and CD, or you could use point D and use vectors DC and DA. It doesn't matter. They're all going to give you the same area of this parallelogram, as long as you pick 2 vectors that start at the same initial point or the same vertex. And on top of all that, this is kind of a weird thing, but I thought I'd mention it. You really don't even need to draw a picture like this to see what 2 points to connect, because even if you chose vector AB and then let's say you picked vector AC, that seems wrong, right? Why would you use that vector? That's not one of the sides of the parallelogram. Well, weirdly enough, the area of the parallelogram formed by these 2 vectors will be equivalent to the area of this parallelogram that I have drawn here. All right, it seems weird, like it shouldn't work, but trust me, it is mathematically the same. Okay, so don't stress about this. Don't get worried about picking the right points. As long as you choose one point to be your initial point and then 2 other points to be your terminal points to create your vectors, you're fine. Okay, don't think that there's only one way to do this problem, because there isn't. There are a lot of different ways that you could do this type of problem and still get the right answer. Okay, but now I'm going to remove that extra vector that I drew. We're just going to be working with vector AD and vector AB in the way that I'm going to solve this problem. Okay, once again, you don't have to use the same two vectors that I'm using, but this is what I'm going to use. And so if you're following along, feel free to use the same vectors that I do. But if you do want a challenge, try using two different vectors, starting at a different point, and see if you get the same answer. But anyway, let's get started here. We want to find the area of this parallelogram, and that's going to be equal to the magnitude of the cross product between vector AD and vector AB. Okay, and so what we have to do here is actually find those two vectors. So let's do that first. Vector AD will be equal to the position vector where we subtract the coordinates of the initial point from the terminal point. So we're subtracting the coordinates of A from the coordinates of D. So we'll have 3 minus 2 for our x component, which will be 1. And then we have negative 6 minus negative 3. That will be negative 6 plus 3, which is negative 3. And then we have 4 minus 1, which is 3. Okay, so that is vector AD. We just subtracted the coordinates of A from the coordinates of D. And then let's find vector AB as well. That will be equal to this vector where we subtract the coordinates of A from the coordinates of B. So we'll have 6 minus 2, which is 4. Then we'll have 5 minus negative 3. That's the same as 5 plus 3. So that's 8. And then finally we have negative 1 minus 1, which is negative 2. Okay, and so now we have our two vectors. Now let's calculate their cross product, and then we'll take the magnitude of that vector. Okay, so let's find the cross product here. Vector AD cross vector AB will be equal to the determinant of a 3x3 matrix, where the first row are the standard unit vectors, I, j, and k, and then the second row will be the components of vector AD, and the third row will be the components of vector AB. So let's just rewrite these components into this matrix. We have 1, negative 3, 3, and then 4, 8, negative 2. Okay, and now let's calculate this. We'll start by looking at vector I. We're going to cross out the row and the column that it's located in, and then use the remaining 4 values to calculate a 2x2 determinant. So we'll have negative 3 times negative 2 minus 3 times 8. Negative 3 times negative 2 is positive 6, and 3 times 8 is 24. So we'll have 6 minus 24, and then we're multiplying that by I. And then we'll subtract the next term, which we get by looking at vector j. We're going to cross out the row and the column that vector j is in, and then use the remaining 4 values to calculate a 2x2 determinant. So we'll multiply 1 by negative 2 and subtract 3 times 4. 1 times negative 2 is negative 2, and 3 times 4 is 12. So we will have negative 2 minus 12 times vector j. And then finally, we'll have some value multiplied by vector k. And to get that, we look at vector k in this matrix, cross out the row and the column that it's located in, and then use the remaining 4 values to calculate a 2x2 determinant. So I have 1 times 8 minus negative 3 times 4. 1 times 8 is 8, and negative 3 times 4 is negative 12. So we'll have 8 minus negative 12. Okay, now if we simplify, 6 minus 24 is negative 18. So this is equal to negative 18i. And then we have negative 2 minus 12 times j. Negative 2 minus 12 will be negative 14, but then we are subtracting that term, so we'll have positive 14j. All right, so we have plus 14j, and then we're adding that to 8 minus negative 12k, and 8 minus negative 12 is the same as 8 plus 12, which is 20, and so we'll have plus 20k. All right. And so that's the vector that results from the cross product of vector AD and vector AB. But now what we have to do to calculate the area of this parallelogram is take the magnitude of that vector. All right, so let's do that. This will be equal to the square root of the sum of these components squared. So we'll have negative 18 squared plus 14 squared plus 20 squared. And this is going to be a pretty big number. Negative 18 squared is 324, so this will be equal to the square root of 324 plus 14 squared, which is 196, plus 20 squared, which is 400. And so 324 plus 196 plus 400 is 920. And so this is equal to the square root of 920, which does have a factor that's a perfect square. 920 is the same as 4 times 230. So that looks like this. We have the square root of 4 times 230. You can check that in a calculator if you'd like. 4 times 230 is 920. And we know that the square root of 4 is 2, so we can just rewrite this to be 2 square roots of 230. All right, and that right there is the area of this parallelogram. That is the magnitude of the cross product between vector AD and vector AB, which represent two adjacent sides of this parallelogram where they both start at the same initial point. Okay, so that's the area. Remember that it would have square units, and if you want the approximate value of this, 2 times the square root of 230 is approximately equal to 30.33. Okay, and so that's it for this example. Let's take a look at another one. Okay, so next up we want to find the area of a triangle that has the following vertices. And we have 3 points, or 3 vertices, points A, B, and C. A is the point 2, negative 3, 4. B is the point 0, 1, 2. And C is the point negative 1, 2, 0. All right, so this example is very similar to our previous example, except instead of finding the area of a parallelogram given some vertices, we want to find the area of a triangle given some vertices. So the process is going to be the same. In fact, it might even be a little bit easier because you have less options. You only have 3 vertices to work with, not 4. And the only other thing that you need to remember is that when you want to find the area of a triangle using the cross product, we want to multiply the magnitude of that cross product by 1/2. The area of a triangle will be half of the area of a parallelogram. Okay, so visually, here's what we're working with. If I draw a triangle here, let's say that this right here is point A, this right here is point B, and this right here is point C. We want to choose one of these 3 points, or one of these 3 vertices, to be our initial point for both of the vectors that we are going to use to calculate the area of the triangle. Okay, so in this case, I'm going to choose to use this vector that connects points A and C, so that will be vector AC, and then I'm going to use this vector as well, which will be vector AB. It connects points A and B. And so just taking the magnitude of the cross product between these 2 vectors would give you the area of the parallelogram that would extend out like this, that whole shape, but then multiplying that magnitude by 1/2 is what will give you the area of just the triangle. Okay, so that's what we're going to do here. In this case, since these are the vectors that we're working with, vector AC and vector AB, the area of our triangle will be equal to 1/2 times the magnitude of the cross product between vector AC and vector AB. Okay, this is what we're working towards in this problem. That's going to be the area of our triangle. But first, we need to calculate the cross product between these 2 vectors. And in order to do that, we actually need to know what those 2 vectors are. We need to know their components. So let's work on that. Let's find each of these vectors. Vector AC will be equal to the vector that results from subtracting the coordinates of A from the coordinates of C, right? We subtract the coordinates of the initial point from the terminal point. So we'll have negative 1 minus 2, which is negative 3. Then we'll have 2 minus negative 3, which is the same as 2 plus 3. So that will give us 5. And then finally we'll have 0 minus 4, which is negative 4. All right, so that's vector AC. Then for vector AB, we will subtract the coordinates of A from the coordinates of B. So we're going to have 0 minus 2, which is negative 2. Then we'll have 1 minus negative 3, which is the same as 1 plus 3, which is 4. And then finally, we'll have 2 minus 4, which is negative 2. Okay, and so that's vector AB. We now have both of the vectors that represent 2 sides of our triangle here. Now what we want to do is calculate the cross product between them so that we can then take the magnitude of that vector and multiply it by 1/2. Okay, so let's work on the cross product. We're going to take the cross product of vector AC and vector AB. That's going to be equal to the determinant of a 3 by 3 matrix that we're going to make up right now. The first row will be the standard unit vectors, I, j, and k. The second row will be the components of vector AC, so these components right here. So we'll have -3, 5, and -4. And then the third row will be the components of vector AB. These three components right here. So we'll have -2, 4, -2. Okay, so now here's what this will be equal to. We'll start by looking at vector I. We'll cross out the row and the column that it's located in, and then use these four values to calculate a 2 by 2 determinant. So we'll have 5 times -2 minus the -4 times 4. 5 times -2 is -10, and -4 times 4 is -16. So we'll have -10 minus -16 times I, and then we'll be subtracting the next term, which will be some value times j, and then we'll add the last term, which is some value times k. All right, let's work on this second one. So we're going to be looking at vector j, and we're going to cross out the row and the column that it's located in, and then use the remaining four values to calculate a 2 by 2 determinant. So we'll have -3 times -2 minus the -4 times -2. -3 times -2 is +6, so we have +6 minus -4 times -2, which is +8. Okay, and then for the last value here, the last 2 by 2 determinant, we find that by looking at vector k and crossing out the row and the column that it's located in, and using these four values to find that 2 by 2 determinant. So we'll have -3 times 4 minus 5 times -2. And -3 times 4 is -12, so we'll have -12 minus 5 times -2, which is -10. Okay, so now if we simplify, -10 minus -16 is the same as -10 plus 16, which will be +6. So we'll have +6 times I, and then we are subtracting 6 minus 8 times j. 6 minus 8 is -2, but if we're subtracting it, then we're going to have plus 2 times j. So we'll have plus 2j. And then finally, we have -12 minus -10 times k. -12 minus -10 is the same as -12 plus 10, so we'll have -2 times k. All right, so we'll have -2k. And now we have the vector that results from the cross product of vector AC and vector AB. We can now use this vector to calculate the area of this triangle. We just need to find the magnitude of that vector and then multiply by 1/2. So let's do that. The area of the triangle will be equal to 1/2 times the magnitude of our cross product vector. So we're going to take the square root of the sum of these components squared. So we'll have the square root of 6 squared plus 2 squared plus -2 squared. And that will be equal to 1/2 times the square root of 36 plus 4 plus 4, right? 6 squared is 36, 2 squared is 4, and -2 squared is 4. And so we have 36 plus 4, which is 44. And so this is equal to 1/2 times the square root of 44. And 44 is divisible by 4, which is a perfect square. So you could rewrite this to be 4 times 11. That's the same as 44. And we know that the square root of 4 is 2. So this would be equal to 1/2 times 2 square roots of 11. But then that 1/2 and that 2 will cancel each other out because 1/2 times 2 is 1. So what we find here is that the area of our triangle is just equal to the square root of 11. That is the area of this triangle. And if you want to know the approximate value of that, the square root of 11 is approximately equal to 3.32 and some more decimals. Okay, and so that's the area of this triangle. Do note that if we didn't multiply it by 1/2, instead we kept that 2 out front, we would then have the area of a parallelogram where these two vectors are adjacent sides. But since we multiplied by 1/2 or divided by 2, the area that we have is the area of a triangle. And I didn't mention this earlier, but very similar to the previous example where we were given 4 vertices of a parallelogram, you don't have to use the same vectors that I used here. You could get this same answer of the square root of 11 if you used B or C as your initial point for both vectors, right? So you could have found vectors BA and BC, and then took their cross product and took the magnitude and multiplied it by 1/2, and you would still get the square root of 11. And you could have done the same thing if you used C as your initial point and found vectors CB and CA. Okay, so there's multiple ways to go about these problems where you need to find the vectors yourself. As long as the two vectors you choose both start at the same vertex or the same initial point, you should be just fine. Okay, and so that's it for this example. Let's take a look at one more example for this video, which is a little bit different than the rest of the examples that we've done so far. All right, so here's our last example. We want to find the area of a parallelogram and triangle given that two adjacent sides are vector v and vector u, where the magnitude of vector v is equal to 3, and the magnitude of vector u is equal to 4, and the angle between vector v and vector u is pi divided by 4 radians. All right, so as you can see, this is a little bit of a different problem than what we've done so far in this video. We're still finding the area of a parallelogram and then also a triangle, but the information that we're given to do that is a little bit different. We're not given two vectors explicitly in terms of their components. We're only given their magnitudes and the angle between them. And so in order to find the area, in this case, of both the parallelogram and the triangle, we have to use a different formula. And these formulas involve using the other way to calculate the magnitude of a cross product. And so those formulas look like this. For the area of a parallelogram, remember that previously that was equal to the magnitude of the cross product between vector v and vector u. The other way to calculate that magnitude is to multiply the magnitudes of vector v and vector u together and then multiply by sine of theta, where theta is the angle between those two vectors. All right, and so that is equivalent to the magnitude of the cross product between vector v and vector u. And so since those two things are equivalent, and that's the area of a parallelogram, then the area of a triangle would just be 1/2 of that, right? It's 1/2 times that same formula. It's still 1/2 times the magnitude of the cross product between vector v and vector u. We're just calculating that magnitude slightly differently. It's a different way to find that value, okay? And if you're not sure where that comes from or how all of these things are equivalent, be sure to watch my lesson video on the cross product if you haven't already. Okay, but with all that being said, let's find the area of a parallelogram and a triangle where two adjacent sides are vector v and vector u. All right, so the area of the parallelogram will be equal to the magnitude of vector v, which is 3, so we'll have 3, times the magnitude of vector u, which is 4, so we'll have 4, and then we're multiplying by sine of theta, which in this case is pi divided by 4 radians. I'll just write that down here. Theta is equal to pi divided by 4, and so we're going to be multiplying by sine of pi divided by 4, okay? And that's it. This is all there is to calculating the area of a parallelogram when you know the magnitudes of the vectors that are two adjacent sides of that parallelogram and you know the angle between those two vectors. So let's calculate this. 3 times 4 is 12, so this is equal to 12 times sine of pi divided by 4, which is equal to the square root of 2 divided by 2. And so now if we simplify, 12 divided by 2 is 6, so the area of the parallelogram is 6 square roots of 2. That is going to be the area of the parallelogram. And by the way, that's approximately equal to 8.49 and some more decimals. Okay, now if we want to find the area of a triangle, we would do the same thing, but multiply by 1/2. So to take a little shortcut here, we can just say this: the area of the triangle will be equal to 1/2 of the area of the parallelogram. So that will be equal to 1/2 times that area we just found, which is 6 square roots of 2, which will give us 3 square roots of 2, since 6 times 1/2 is 3. All right, and so that is the area of the triangle. And once again, I'll give you the approximate value. That is approximately equal to 4.24 and some more decimals. Okay, and so that's all there is to this example. It was kind of a quick one, but I did want to make sure to include it in this video, even though it's kind of a rare problem as well. Typically, you're not going to be calculating the area of parallelograms and triangles using vectors in this way. you're more likely going to use the cross product in the more standard way, the way that we calculated it in the first 4 examples of this video. Okay? And so with that, this was the last example for this video, but if you do want to see another example, I have another available on my membership site, and so feel free to look into becoming a member if that interests you. If you have any questions, feel free to leave those in the comments, but if you don't have any questions, this is all I had for now, so I will see you next time.